is I gotcha. I've been a student here at City College for a little bit. Maybe that was 5 years ago. I was sort of having like a, hey, I should do something different with my life. You know, I've been in finance and technology for a long time, and I wanted to kind of get the idea of I should try to teach. And so I took a couple of math classes here, and one thing led to another, and I was teaching a high school math class. It was kind of fun, but there was a lot of, emotional drama, which I wasn't prepared for. So I ended up back here with the idea that, hey, I might as well in my break learn a little bit about AI. So I kind of had it in my mindset that there was this curious thing about AI. I want to learn more about it. And so today I'm here to talk about that. I want to first thank Mr. Sean Wiggins here for setting this up. Okay. And, bringing a real cool audience here. For me, this has been an exciting thing because it's been a while since I've made a presentation, honestly. In the old days, I used to present, but it's been a while, so it's kind of fun to prepare something for you guys. So let's just get at it. And the stuff about AI is born by this free online class I've been taking, okay, called CS50 AI. And it's been a great learning experience. It's a very wide-ranging topic. And I'm not going to lie, it's really, really hard. There's a lot of math involved in it. But what's really cool and exciting about it, this field of AI, is that it ties together all this great content that you could learn right here at City College. So, like, the foundation for all this stuff I'm going to talk about is stuff I've really picked up in Math 108 and 110 calculus. There's stuff in discrete math that seems so obscure, and a lot of computer scientists are going to have to take 115. It seems so obscure at a time, but it all kind of like comes to play. So we're going to talk about words like state machines and vectors and dot products. And, sometimes when you're talking about recursion in your data structures class, it just gets so obscure, and you're just like, well, what are we doing this for? And then, you sort of build a project like, oh, okay, I get how these pieces start fitting together. So I think that's pretty exciting. And the whole Sudoku thing starts out for me is that in the third week of the class, we're discussing something called constraint satisfaction. Now, constraint satisfaction is a type of algorithm that's used in industry, typically for solving what we call scheduling problems. So imagine the software that it takes to do the university scheduling here. All the classes got to go in which room. They can't collide. You can't, there's constraints, right? If there's a classroom here, another class can't be in it, right? Your schedule, my schedule. Think about an airline. How many planes are in the air at one time? You got to figure out when it's going to land. You got to schedule all this stuff. This is all constraint satisfaction problems. But there was a comment that said Sudoku can be thought of as a constraint satisfaction problem. And right then and there, this big light bulb went off in my head. Bingo! Because I thought to myself, well, finally, I can solve this silly, coding challenge. Okay, so that takes me back before my time actually at City College, when I first was kind of self-teaching myself Python, hacking around. I learned about something called Project Euler, and there's something called LeetCode. Okay, you guys probably know about that stuff. So Sudoku is a well-known challenge. Okay, but at the time, I mean, I tried, but I just couldn't get there. I didn't really have the tools. I had sort of like figured out I was playing the game, but I kind of knew the rules, but I just couldn't get the solution. And the moral of the story is, of course, go to City College. Because once I read that constraint satisfaction, this is how it works. At this point, I had the background because I knew about graphs and state machines and sets. Okay, that wasn't a language that was familiar to me. I knew about data structures and recursion, depth first search, and so I was really able to bang out the code literally that night. Well, technically not that night, because that first night I ended up in recursion debugging hell. Has anybody ever been there? Where you try to write something recursively and sort of like your inception and can't figure it out, Well, I was in hell that night. And the moral story is the next morning when I woke up, first thing I was thinking about was Jessica Masters. What did she tell me in data structures? That you could do recursion with a stack. And bingo, the next day, put it together as a stack, works. So that was kind of fun. Now, by the way, you get all excited about it. Hey, I can finally do it. You write the code, you put in the solution, you find out you're the 19,000th person. It's not like, it didn't feel like very cool to me at the time. And then when I ported my code to leak code, I was 600,000 submission. So this is nothing unique, okay, but it's still a challenge. I didn't cheat. It was all my own kind of ideas. So, even if your code that you write when you go off and do a project isn't original or isn't particularly cool, it could be cool for you and the thought process and the learning that you're going to have. I mean, I really want to encourage everybody here to do that, okay? And don't worry, that's not cool enough, okay? Now, for me, the Sudoku thing, by the way, does everybody know what Sudoku is? I should probably, okay. So for those who don't know, just a real quick refresher, it's like a crossword puzzle where every row, right, and every column and every block has to have the numbers 1 through 9. It's called a constraint, okay? But when you look at these coding challenges, the issue is we have text-based character entry, right? If you look at like the way they look, here's a Sudoku puzzle. It's a string 001, 007, 002. I mean, to me, that's geeky, right? I mean, if you actually see a Sudoku board on the newspaper or your phone, you're not looking at it that way, right? And if you're going to say, hey, look, I wrote this cool piece of code, I got to tell it, look, the board today is 001, 007, right? What we want to do is take that image that we see and give that JPEG, right? Like, just give the picture. I don't want to give this. That's what, that's like computer land. I want to give this, right? And so think about it. And today, this image processing, this image recognition stuff is like at the heartbeat of autonomous vehicles. Cars going around taking like 100 pictures, picture every second, right? Think about medical imaging. Do you have cancer or not? It's analyzing the X-ray. But it's doing it. It's doing it through image recognition. So let's talk about how to do that. So right now, I want everybody to open up their Google Colab. So let's start coding. And I'm going to switch to. Okay, is everyone there? All right, yeah, I want you to take about a minute or so, everybody, to just play around and see what this Google Colab thing is. Okay, Google Colab is a cloud, yeah. Yeah, okay, you can do this. Sorry, thank you. If you would like to save a copy of this on your own drive, there's a little button here, copy to drive. Okay, so if you want to save your work, you can copy and save, but I think if you take the link, it'll just make a copy and you could work on it on the fly, I believe. What can I tell you about a Colab? A Jupyter Notebook. A Jupyter Notebook is kind of like a document that's half document and half code, right? So it's like a web page, and like these are text cells. They're sort of images and text there, right? It's my communication to you to make this look more like a document, so to speak, right? But in the next few cells, if you scroll down the page, we're going to come eventually to something that's slightly different. There's a little gray here and there's a little arrow. And this is called a code cell. Okay, so there are code cells and text cells. Text cells are just there. You could edit them, but they don't actually run on the machine. But once you get to a code cell, we're talking, this is Python. Okay, so what I want everybody to do is just go onto that code cell, click it, select the code cell, and either hit the arrow. This means play or run your code cell. The Python interpreter will read all the lines and execute them one by one, right? Or the shortcut screenshot, the screenshot shortcut is a shift enter. I'm going to hit shift enter here. And notice it's going to give me a message that there's a warning. I'm going to say run anyway. And the first line What it does, it runs a bunch of code that sets everything up for us. But while it's loading, let me just talk about what it's doing here. We are importing industry standard packages. One is called NumPy. Okay, what's nice about Python's open source ecosystem is that you don't have to pay for anything. It's all open source. If it's not on your computer, you say pip install TensorFlow, pip install CV, pip install whatever. You can just install these things. And once they're installed in Google Colab, everything's installed for you. If it's ready to go, you just say import NumPy as NP. And now suddenly what we brought in as NP is all the required plumbing to do high-speed data calculations in NumPy. The second line here, we are importing something called matplotlib, okay, which is a package that lets us do image processing. Well, not really image processing, but basically gives you the tool to plot things in a Jupyter Notebook. This is something that works well with Jupyter Notebook. We have CV, OpenCV. Okay, if you go to this website, you'll see a huge library of stuff that work with Java, C++, Python, that are all like the components of computer vision and little processing. We'll talk about what kind of algorithms. We're going to use it to do things like open a file, like how do I get a JPEG? How do I deal with a PNG file? How do I deal with a BMP file? I just use OpenCV and just say read it, and it gives me a NumPy array. It does that kind of dirty work for me, all right? And then finally, the package we're going to use is TensorFlow. You know, we import TensorFlow as TF. And what TensorFlow does, it's an open source package that lets us kind of write these complex neural networks that we don't even really need to know exactly what's going on in the hood. It just sort of like does everything for it. So it sort of lets us play at a higher level. Okay, we have to think about what a neural network is, but we don't have to be the mathematician that figured out how to write the back propagation algorithm. Kind of like already there. All right, so that's what's there. So you run that piece of code, hopefully. And before we get into image processing, the first thing we're going to talk about, if you never really worked with images, is that if you have, let's say, the number 8 or a picture, how is that, like, what does that actually look like? I mean, we know what it looks like to us, but how is it stored in a computer? And what's stored in a computer is just like a 2-dimensional array of numbers. It's just numbers. Each number represents a pixel. So imagine this thing is an 18 by 18 array. And if this was an 18 by 18 pixels, you just make 18 little squares across, 18 columns down, right? A number 0 means absence of light. A high number is full light. So we're in an 8-bit color space. That's why the highest number is 255, the lowest number is 0. So we work in between 0 and 255 in terms of what that number is. So this is saying, hey, that's white. And notice you can see the pattern here, okay? But what's important to remember about image recognition is that 8 is going to look like an 8 to us, whether it's shifted to the right, left, up, or down by 1 pixel, we can't tell. But to a computer, hey, if that 113 is up there, that's a big deal, right? That's not the same, right? What does it know about a picture, right? So even by just shifting this registration of the 8 a little bit, or stretching it or moving it to us, our eyes, it's nothing, but to computers, it's a lot different. So it's something to keep in mind. All right. Now, the next line of code demonstrates how you would use OpenCV. You give a file name. I'm calling OpenCV. Anytime you see CV dot, that means I'm using CV. Anytime you see TF dot, I'm using TensorFlow, NP dot, etc. Right? So this is like asking CV to open a file for me and read it. And by the way, I've kind of written this in a way because it works in Google Colab. If you click on that little icon right there, which is the file thing, I've tried to organize all the files that this demonstration works in nice little folders. And this file, I call it MPath. This directory, I call SPath, all the images. These are various screenshots I've taken. And this is where my training data is, okay? So I use, just to make it all work on a Google Colab, I needed to put these little annotations like SPath plus a file name. Okay. Otherwise, you won't be able to find it. Just run the code. Let's see what it does. So this is basically all it's doing is getting a picture and then showing you the whole contents, right? And notice the screenshot I grabbed is a full, like a web page, right? It's got a lot of stuff. Now, you and I, we all know the Sudoku board's right here, right? And if we're going to go off and say, I want to recognize this board, how do we find here out of the whole space, so to speak, right? There's a lot of numbers out there. How are we going to find it? This is where OpenCV comes in. And this next code cell here literally just gets copied right out of the internet. If you Google OpenCV, how to do contours, I just copy that code and check it out. Boom. Like OpenCV has routines that go up and analyze gradients and changes in pictures and make little lines. And then it's up to me as the software engineer to say, hey, okay, let me understand what this contour object looks like. It turns out there's like 700 contours on this page. I sort them by area, size of area, and I say, let's look for the one that's a square. And I'm gonna just hope and pray that that's my Sudoku board. So if I gave an image with a big square out here, it's not gonna work. It's gonna, find that. So my code just looks through these contours and says, find the biggest box, isolate it, and then do some, let's say, maybe switch the color space. We'll talk about why we do that, but I did this because it turns out the data set that I have for training on numbers kind of looks like this. So you have to sort of like match your data to look like what you're trying to do. Make sense? Okay. Once you're able to do the job, remember with OpenCV and the contours, isolate it. There's all a little bit of math in there, but not hard math. We're able to do something like that, but to say, hey, how do I find this number or that number, right? Well, this is an array that's indexed by position, right? So we have a row coordinate and a column coordinate. And to give you an example of how do you go off and zero in, remember, like every image, this line here gives me the shape of the image. So this is saying this is actually 497 by 497 pixels wide, right? So let me just take a look at what the 50th row to the 250th row. I'm just let's play with some numbers. Just changing numbers in there, right? So if you do that, what's going on? You're zoning into a different part of the image, right? We've essentially snipped in to some part of the image. That makes sense? Yes. Okay, that's a long conversation. Okay, because initially I tried to write my own code to find the line, and I actually looked at the variants, and I actually tried to like build something myself. It turned out it didn't really work very well. And really just imagine what all I literally did was to take a paintball roller, like a paint roller of black, and just say about every 10%, I'm gonna run a paint roller of black across my image. Does that make sense? So it's sort of crude, okay, but I was just trying to get some of the work. And then I have this, once you sort of figure out how to use coordinates, you can write another function that sort of abstracts the idea of, okay, how do I find the first row, fourth number? Okay, so now you write a function called getSquare where, boom. Okay, so no matter what you do, you can try different numbers here, different coordinates. You should be able to get that block that you need. Okay, so these are sort of like the building blocks as you approach this project, like, hey, how am I going to recognize? First, I have to identify the board. The next step is I need to get the numbers off the board. Now, what's the next step? The next step is saying, hey, look, I got this image. I got to tell the computer, tell me that's a 9 and not a 6, right? It still doesn't know how to do that. And that's where convolutional neural networks come to play. So I'm going to talk a little bit about what that's all about here. Let's see. Let me, for some reason, oh, there we go. All right, neural networks. First of all, what's a neural network? The word neural is actually inspired by biology. The first neural network research paper, I think, came out like 1960. And what they're looking at, what's the structure of a neuron? They had neurons have, I think they're called axons. Anyway, they're connected to other neurons. Okay, electricity is in one neuron. And one neuron gets like 8 or 9 different signals. Based on the signals it gets on, it passes on another signal to some other network, so other neuron. So they try to figure out a mathematical model. Say, you know what, let's just see what happens if we try something like that. And that's sort of the idea. But let's see, convolutional neural network is just a variant. We talk about the variation that actually turned out to work very well for image recognition. Pretty much anything that's doing image recognition today is using this kind of technology. But I want you to think of neural network as like linear regression on steroids. It's like an amped up version of it. Because in STEP class, you might learn that what you're doing in a linear regression is you're taking data, right? And you're fitting a line. You're trying to fit a line of best fit. And then we're using that line to make a prediction. But here, what we're doing is we're finding the best function. We're not finding a line. We're finding some weird, wiggly, something that we don't really even understand, but somehow it can classify stuff. It's some weird function. Okay, and then we're going to use that function to make predictions. Okay, so it's very similar regression. You're getting data, right? You're creating a line based on that data, but here we're taking our data and finding that function that best fits the data, and then use that function. Okay, and the reason why they call it a neural net, they try to make this like tangle web of connections. Okay, in this particular diagram, what we have is an input, and then finally we have an output. What makes it a neural network is we have what we call these hidden layers in between. Okay, these are sort of like stuff that the engineer makes up. Oh, I'm going to put 3 layers. I'm going to make it this big that way. Okay, the way the layers are connected is mathematically is through a matrix multiply. So this vector. So if you think about your input, this is 3 inputs. As an example, a 3-input model might be something like, I'm going to predict if it's going to rain tomorrow. This is my rain prediction. But my input is today's temperature, humidity, and pressure. I'm going to put those variables in. I'm going to do my matrix to here. Okay. And by the way, it's a matrix multiply with a little activation function in between. But if matrix multiplication, I see people already like, I start to close when we talk about that. You think about it this way. Each node in the network, right, is a weighted sum of the previous layer, right? Does everybody know what a weighted sum is? If I had weights of 1, 1, 1, it would just add these 3 up. If it was 1/3, 1/3, 1/3, I'd be taking an average of those 3. If I said 1, 2, 3, you know, it would weight this one bigger, right? You're just taking weight, you're just making another column, multiplying those numbers, and then adding them. It's a dot product. Okay, but you have these, this has a weight, this has weights, every node has weights, right? But while this is a simple picture, the one that we're using with the tiny little number 8 is 28 by 28 pixels, meaning that the input layer is about 800. There's 800, and then it goes to like 5,000. It's like crazy number of numbers in there. Okay, so many numbers that no engineer could say, hey, you know, my model is going to have these numbers. That's the one that works. We don't know those numbers. We just know that there's a lot of numbers in there. Okay, and the idea is we go off and we create this model. It could be a complete guess. We say, let's test it. Let's crunch out all the numbers and see how close we are. We find out a loss. And then we're going to use some calculus to say, hey, look, I'm going to minimize my loss by moving all my assumptions to slight direction. And we're going to just do it over and over again. That's part of the idea. All right. Is everybody with me? Yeah. Yeah, I know. I thought that I probably should just kind of do it online, but it's nice to talk to people, right? So let's talk about training. You know, it's sort of in the news, you know, like models need to be trained. Like, what does that mean, training, right? We stick the computer in front of stuff and train it. In some ways, it's trained, but maybe a better word is fit. We're sort of like fitting our model is probably the better word. And what we're going to do today is something called supervised learning. Okay, supervised learning. Supervised learning is what means when we give data to the computer, we know what that data is. So in other words, if I have a picture of 5 and a 2 and a 1, I also have information to tell the computer that image is a 5, that image was a 2, that image was a 1. You got to tell it the truth so it can kind of learn, right? And then once you kind of take away that truth, can it guess based on what you've told it? Does that make sense? Where we're going for? The point that I did want to reiterate was that because these matrices are large and we really don't have a clue, the idea is we start with a complete guess. And then we go off and we calculate a loss, and we're basically using calculus. It's called gradient descent. And this is where the, follow the derivative idea comes in. When you're on the graph and you don't know if you're at the bottom, you're at the minimum of a function. If your derivative is not 0, you go, hey, which way is the derivative going to take me, left or right? And you just follow that. And in a nutshell, we're doing it in like a multi-dimensional way, but we're basically following the derivative to minimize the loss. We're going to do it in very, very small steps. And today, what's kind of crazy is that it's actually randomized. They found out that it takes so much computing time to figure out this complicated gradient. Okay, here's another idea that's coming from stat class, is that rather than taking all your data of pictures, we're going to sample, we're going to subsample the data, figure out the loss. So we're kind of like not really finding out the real loss, we're finding out like an estimate of the loss based on a sample of the data. And then every time, and it allows us to iterate faster, okay? And it turns out to work. And it said, you repeat and you repeat and you repeat until you find a solution, and hopefully it works. The last point about this whole process is that there is a large risk of overfitting. So neural networks, it turns out from what I've read, and through experimentation, you could figure out yourself actually, is that it's sort of easy to get the model to say, hey, I know all the training data, but it's not always so obvious how you get it to extrapolate from that to a wider thing. So let's all go back to our Google Colab now and actually train a network. Let's actually put a network training. All right, so this is where we stopped. We had gotten to the point where we had enough parts to say, get me a picture, find the Sudoku board. Now I can find every little square that I need, 81 grid position, right? And next step is to build this convolutional neural network. Now, I pulled out this diagram from actually an image research paper, like a medical research paper, but they're using almost the same, what I would call topology, as what's presented for a digit recognition code. So if you look at it, look at this code right here. You don't have to understand what it means. I didn't, and I still don't. All I did was just take boilerplate code that this class is giving me. Hey, try this for digit recognition, it works well. Try this, we can modify things. So if you wanted to, as an example, to add a convolutional layer, like I could just repeat a few of these lines, just cut and copy. Just try it again. If I wanted to add another layer in between, just cut and paste this dense layer, make another one, right? If you want to change the activation functions in between, I talked about activation function, change activation from RELU to something like called sigmoid, okay? So there's different things, but the truth is I found that better just not to play with it, just run with it and see where that goes and then play with it later. You could do that. So we could run that piece of code. And so I'm going to run that. And then this next line of code, what it's doing is actually going right into TensorFlow. So TensorFlow, so all these like AI packages often come with, let's say, sample data for you to get started with. It's hard sometimes to find data. So there's this famous data set called the MNIST. If you Wikipedia it, I'm sure you'll find, I'm not exactly sure where it comes from, but there's a lot of numbers. And it's it's available without having to work for it. It's part of the package. And I wrote something right here that lets us go off and take a look into it. So Vue 28 goes off and says, okay, give me the first 144 images that are contained in that data set. So this is what actually our training data set looks like. And the size of it turns out is 60,000. So there's 60,000 digits handwritten that somebody has laboriously labeled as the correct answer. Okay. And so this line of code, what's going to do is it's going to create a brand new model. Now remember, when we create a model, what are the matrices? Well, the weights, they're all random, right? The next line is going to evaluate that. And we're going to actually use the model to see how well it predicts. So if I were to create a brand new model and run the evaluation, like what's here, this how long it takes to, and I see some accuracy numbers, says accuracy 8.5%. So out of all these numbers that it actually tried to calculate, it only got 8% right. But that seems about right because it's a complete random guess at this point, right? And this next line is where the magic happens. We're going to take our training data. This is minced model. Remember, the minced model is an object. And one of the API for an object, remember, is to evaluate, predict, or to fit. Okay, so we've shown evaluate. We created it first. We've evaluated. We're using mincemodel.fit. Thank you very much for that. Okay, so if we fit this and run this code, let's see what's going on. Everyone do that. We see this weird thing called an epoch, and the computer just starts crunching. And notice the accuracy number here to the right. It's like creeping up. Like the more times it crunches the number, it's getting like closer and closer and closer to finding something that works. So this is what it means to train a model. You're basically running through. And what I did here was to make the training go much faster by above with this ... 5, that's called data striping, where I give what I'm, instead of passing the whole training set, I'm saying just take every fifth. Okay, just for speed. Okay, just for a demonstration. But I could change that back to nothing. And you could try epochs like bigger epochs. Epochs 5, epochs 10, okay? And just so everyone understands the language, I didn't understand the language either. I had to do a lot of research and preparation for this talk, actually. Like, what's an epoch? Actually, turns out an epoch is when you've been guaranteed to go through your entire data set once. So remember, I told you that the way the algorithm works is that, hey, there's too much data there for me to deal with at once. I'm going to random sample in batches of 32. And once I finish my first full batch, full sample across your whole data set, that's one epoch. Okay, so there's no real good, I think this is something where you just have to sort of play with it, right? And luckily, the next line of code lets me just save or load a model from disk because it takes a long time. The model that we're going to load up in this next line, it took probably in Colab more than 5 minutes just running it, maybe 10 epochs. Okay, it takes more than 5 minutes. And let's try evaluate. Let's see how well this particular model works. So remember, we started about 8%, 99% accuracy. Okay, just by going through the data, you'll see by training your model, you can make your model more effective. Now, let's take a look just a little bit like how these predictions look like. If you're writing the code, like what do you actually get? So one thing to keep in mind is that this prediction array that we create, our network actually, the last node has 10 layers. We don't say the last op, we don't say, hey, give me the number it is. We don't say, give me a 0, 1, 2, 3, 4, 5. We have 10 different ending places called one hot. I think it's called one hot, something like that, where you make a position for every result that you want. So if you want to, let's say, have like 40 categories of traffic signs that you want to try to classify, your end layer should have like 40 certain dots. And for us to be 10, so that's why we have this 10-digit array here. I just want to, I know it's kind of obscure, but I want to talk about it. Notice that all these numbers, they all have like these like crazy looking scientific, they're all zeros. The first number is like a 4 with 18 zeros in front of it. The next one is like a number with like 17 zeros. And then finally we get to a number that looks like 1. And really that's the 7th number. So that's what NP-argmax does, is like, find me which number is the biggest number. And so 7, it predicted 7. So that's basically what you need. Once you have all this, then we have all the building blocks to go off and build, let's say, a function called read Sudoku board. Okay, that would be sort of like tie everything we've done together, right? Like we've gone off and pulled from, CV2 to read the board, right? We've done find contours to find the grids. We've broken it up. We've packaged it into a nice array, and then we output. So let's give it a try. So I'm going to take this picture that has a lot of numbers in it. It's like a full model. And if you take a look at this, just examine what happened. And I'm looking at the results and I'm saying, hey, you know what? It's actually kind of good. It actually classified most of these numbers correctly, even though those digits, I mean, the weird thing is when I first tried this, I was thinking, I don't know if it's going to work because the digits don't really look anything like the numbers. I mean, how accurate is it going to be if we get trained on handwritten digits and the digits that I'm showing you look like that? And unsurprisingly, it's pretty good, but it's not good enough. Okay, and at that point, I remember I was writing this stuff. I was like, oh man, this is not going to work. And then I thought, you know what? What the hell? Let's try to train it ourselves with our own data. So how would you do that? I thought to myself, well, I could just get pictures of Sudoku boards and just type in the numbers that it is. And I already have all the code. Remember, we already have the code to find the Sudoku board. We already have the code to find all the numbers. So all I got to do is write a little more code and say, this is what those numbers are, guys, and then use that to fit the model. So that's what we're going to do. So if we come up to the next cell, you don't have to understand any of this code in here, but I try to make this a little bit interactive so that we can all do a live experiment. Okay, so I have 10 training pictures, okay, in that little directory that you could take. And just by turning these on or off, we could decide how many of them you want to include in your training set. So I'm going to turn a couple of these off, and I'd love you to just experiment and turn some off yourself. I'm going to call this false. Maybe I'll call this one false. So instead of training on 8, or maybe I'll give it 7. Here, I'll just say false, false, false. And if I run this cell, what do I get? You'll get, let's see, you'll get like a visual representation, just sort of like a picture of the numbers that I pulled from those 7 boards. And one other thing that I put in here was this idea of synthetic data. I'm gonna give you a little picture of that. Okay, so oftentimes collecting data in the real world for data scientists is difficult and it's costly. It's a pain in the butt. You know, you have to go out there, you have to not only observe it, measure it, you have to say exactly what it is, you have to put it in the format of the computer, and then you have to feed it. I mean, it's a lot of time and effort, human effort. So how do you amplify data? Well, I take that number 2, 6, and 3, and remember we took a little camera shot of it, and what I say is, I'm going to jigger that camera. I'm going to move it to the right, I'm going to move it to the left, I'm going to make it shrink, so that 2 comes out of all these different 2s. You know, I know they're going to all look like the number 2, but somehow I'm going to give more data by sort of creating synthetic data. So that's kind of like how that part works, all right? So with these 7 boards, what we should be able to do is train the model again. So here we go. This time we had a minced model, but now we're going to create a new model. We'll call it our model. Now, if we try to run our model against this board, what's it going to do? Well, actually, it did a terrible job recognizing, right? Because it's, I don't know, it's weird. Mine just says 1, 1, 1, 1, 1. I get nothing, right? So, but of course, it hasn't been trained. So I'm going to run the next cell and fit it. Oh, is anybody training their own? No, it's like too fast to follow along live. It's like too much, right? Anyway, I would like you guys to go off and try this later because it's kind of cool. Like in the beginning, my journey started out with actually only 5 pictures and I got it to work. And I thought, oh my God, this is going to be great. And then I tried to show it to somebody else and was like, oh, made a mistake, you know? And so you have to be sort of careful about this, but it's doing a few epochs. Look, the loss has gone down. It's gotten smarter. Okay, in fact, it said the accuracy is 100%. I'm not sure. First of all, you have to take these things with a grain of salt because it's accuracy based on the numbers that I gave it. You know, maybe it's going to see something that looks very different later, or somehow that it's just something you just don't know, right? And anyway, what's that? Oh, a couple people trading online. All right, well, let's just see how this particular one worked. Look, it picked up the 1, the 6, 7, 4. I mean, to me, it looks pretty good. For just training off 7 images, I'm able to get another board that it hasn't seen to nail it, right? So I think that's pretty cool. Anyway, we can all pull this train model. This next cell tries to get us all on the same page by preloading that train model that I already have done for you. I don't want to waste like 3 minutes just sitting there waiting for it to calculate. So at this point, we're ready to talk about how to solve a board. Maybe this is a good time just to pause. Did everybody, any questions on, I know we went really quick through this whole idea of what a convolutional network is, how we got data, how we trained it. Then we tried to see how it did on our information. Then we went off and took our data, right? We started off with image data. We trained 2 different models. Who's with me and who's just completely lost? Are we good? All right, okay, all right. Now we come to a different part of AI. Remember the first part of AI that I wanted to introduce, open the door for you was convolutional neural. That's that image processing, right? Now the image processing has been done. Let's assume that this works. Okay, so I've read my board, right? Now the question is, how do you solve a board? Like, how do you go off to write AI to solve a board? Like that's a puzzle, right? Like it's a different kind of AI. And I want to talk about a couple of different topics here. I'm gonna, let's see. Okay, so we're gonna talk about words like search and graphs and neighbors and something called constraint satisfaction. You know, big kind of like CSE type words here at this point. Yeah. Yeah. Yeah, you know what? I'm gonna just say I'm gonna punt on that because when you're scripting, there's gonna be a lot of errors in the code, and so if something breaks at this point, I'm not really sure I can without looking at it. Sure. Yeah, there's something there probably there easily could be because I've rewritten it so many times and refactored it and brought different things to different places. So something might have broken. So I apologize about that. Anyway, so since everybody knows what a Sudoku board is, I want to bring this idea about domains up because when I saw that word, I was like, wait a minute, am I back in Math 90? What's a domain, right? Like the domain of this function, right? Well, here's where it really kind of comes into play. It's kind of cool is that you can think of every empty cell as a variable, and the domain is the set of things that it could be. So in other words, if I had a completely empty board, every domain is the characters 1 through 9. Any board can go in any position, but here, as an example, what's the domain of this cell? Well, it can't be anything that's in its row. It can't be anything that's in its column, or it can't be anything that's in its block, right? So we have this really useful set operation expression. This comes from math, right? Where you could say the domain of this cell is the set of all its row, union with the set of its column, union with the set of its block, right? And then take the set complement of that. And that's 1, 2, 5, 9. So from a coding standpoint, all you have to do is look, gather up all your cells, all the numbers in there, gather up all the numbers there, and gather up all the numbers in there. And whatever numbers aren't included, that's your possibility. That's a domain, right? You write a piece of code like that, boom, you could apply it to every cell, right? Then the next step would be to think about, hey, wait a minute. Turns out you might find a domain that only has one possibility. What happens if a domain only has one possibility? That means the only number that it could go there is an 8. So that's called an inference. Mathematically, you call that an inference. Stuff that we're learning in this AI class is that you go off and put that, assign the 8 because you can make an inference. And the interesting thing about mathematics of inferences is that once you make an inference, it changes the inference, it changes the domains of the neighbors. Okay, so I put an 8 there, and here, before I put an 8 there, this domain was 7 and 8, but once the 8 goes here, I have to scratch this off because I can't fill, and once I put an 8 here, I can't put it here. Okay, so there's this idea that your inference, the inference that you can make changes as the state of the game changes. And now I actually want everybody to go back to the Sudoku. I mean, to the collab. Okay. So I've read the pseudo. And by the way, I've written this class called the board. Sorry. Where am I here? I've written a class called the board that I've written a method for, like having understood the issues that are going to come up, that's called unassigned domain. And that what means is just go through every cell. Anytime I find an empty cell, give me its domain. Okay? And in fact, I can sort it. So if you do something like this, this is saying, okay, here's all the domains I have left. And I'm sorting it by the length of my domain. I'm saying, hey, you know what? These 3 are 1. What should we do when we have a singular domain? Well, we should put a number in there, right? And so if you look at, sorry, okay, I'm going to just scroll down. Thank you very much, Sean. If you look at that list, we write code like this. Here's a Python loop. I say for cell domain in pseudo.unassigned, so give me that big list, and I'm going to iterate through that list. And for every time I find that the length of that domain is 1, if I only have one number, what am I going to do? I'm going to get that number off the domain. That's my little pop, and I'm going to sign it. Okay, I'm going to sign that board position and put a number in there. So let's just run that cell. I'm just going to assign those 3, right? And then if I look at the unassigned domains, look, it changed. Remember, we only had 3 singular domains before we started this. We made our inferences, and suddenly we have a different set of unassigned domains. Well, logically, do you think we should just try that again? You follow where I'm going with this, right? We could just make a loop of this, right? We could just say, let's run it again. What happens? Oh, you know what? It's gone off and found a different unassigned domain based on the new inferences it's making. So we could just keep looping and say, hey, look, every time it finds something, just keep rerunning the cell. And where do you go? Turns out, as you may expect, this is going to end up in something where, wow, we're going to get there, I believe. It's an empty, there's no more unassigned domains. If I print pseudo at this point, what happens? I have a solution. Okay, so that's one way of thinking about the problem. Now, when I was trying that Project Euler 96 years ago before I came to City College, that's as far as I got. I got some boards to work. Like that's not, the harder part is there's sometimes, you don't get to do inference. Sometimes there are no singular paths, right? So let's take a look at this one. I'm going to read a different board that was classified as a hard board, right? And when I did the unassigned domains, this one, you notice ready from the very first, there are none of these. You can't make any inferences off the bat. Okay, there's like, there's no option. What do I do now? Okay, and here I would like to take a moment to just talk about, I want to talk about graphs. I want to talk about graphs a little bit and state machines. Okay. These are sort of like not in the best order. I want to go to this slide here. States and graphs, state machines. Okay. in Math 115, Sean Wiggins introduced me to the idea called a state machine, and one of the things, and it turns out it's a very useful mathematical construct for thinking about games and puzzles. Okay, so every board, so I want you to do this. Take this little mental thing where you imagine the Sudoku game as a sequence of filling in empty squares. So you're starting with a board, right? Then I fill in a square. Then I fill in another square, and I keep filling in squares until I get to the end, right? So it's a sequence, right? And what you think about it is that you use that assignment, that filling, as your transition from your one board to the next board. So these are where states come into play. You have one board that has a fill. The next position that every time you fill, you change the state of your board, right? So now you can start thinking about, hey, it's a graph. Okay, I have vertices and edges. I can think of like the boards as vertices and the edges as being my transition. Okay, every time I do an assignment, every time I add something, I change the state of the board. This is like, hey, you can think about it in terms of graph. Now, why would you want to think about it in terms of graph? Because actually there's a lot of algorithms for graph search. So, I mean, I will tell you, that's one of the biggest takeaways for me taking this AI class is like, hey, when I was in the math class and people talked about a graph, it was all about, oh, there's some proof or some theorem or find this thing. And it was the graph was given to you. Here's a graph, do this with it. Whereas more often, the way you're going to use a graph is you as the engineer have to imagine the graph. Like there is no graph in a Sudoku board unless you sort of, hey, you know what? I could use graph thinking. If I use graph thinking, then I could use things like, hey, DFS, depth first search, okay? So in constraint satisfaction problems, there's something called backtracking DFS search. Now, if you've been in master's class, you're gonna have seen something like this where you see a recursive algorithm. This is like something I just pulled off the internet. This very simple idea, but look, procedure explored node n, if reject, then return, complete, then you output. And then it says for n, children do explore. This is not even any language I understand, but it's just pure pseudocode. But what's telling me is this is like a recursive algorithm where you're going off and then calling yourself and then calling yourself again, and you're going into that sort of inception mode. But like I said, sometimes for me at least, that's hard to do. So that idea about Jessica Master is as, hey, turn that recursion into a stack implementation, right? And here, like the pseudocode for stack would be, you create an empty stack, and then you just repeat the process. You say to yourself, if the board is complete, I don't do anything, okay? But then what you do is you get all the edges from your smallest domain. So you go around and look at your board and say to yourself, okay, where is the place that has the least choices, the fewest choices, right? I mean, as a human, that's how you would play. You would basically use the constraints to sort of, essentially with the idea of constraint satisfaction is you're using the structure of the constraints to limit your search. There's a lot of assignments I could do. I could put a 6 here, I could put a 4 here, somewhere else, but why not choose the cell that has like a domain of 2 or a domain of 3? Why not start your guesses with the smallest possibilities? You're more likely to get correct, right? When you go and search a path. Whereas just a blind depth first search would be, look at all my children, the first one, I go look at that one. Look at all my children, first one. With constraint satisfaction, you're saying, out of all your possibilities, let's narrow it down. We're using some heuristic and still use the basic idea. So I'm going to just leave it at that. That's the end of my talk. There is a copy of that algorithm right out there. So anybody who's in 111C, I expect you to be able to do Project Euler after this. You got the pseudocode, you got some of these big ideas. You know, now it's up to you to put it in, implement in C++ or C. And if we go finally back to my little code cell here, let's just run it. Where's the coup de grace on this thing? Of course, the final, let's see, this one right here. That hard one, what's it going to do? It's going to crunch. It's going to think about it. Actually, it turns out it's going to take a lot of paths. You know, I have like a flag in there that shows me the history of the paths it took. It took a long time to figure that out, but it does sort of like plot out a solution. So that's it in print. Thank you very much. Let's see this last code. This is going to iterate over that whole list of images in there and just do them all. Okay, just to see if it works. So it's just going to run through that directory of 15, 20 images, and just if it figures that out, crunch it out. If it doesn't, you'll see that it didn't work. That probably means that what it means is if it didn't solve it, it means there's something basically happened wrong in the image recognition, and it concluded that the board was unsolvable. They just never found a solution. Probably because it read the board wrong, the starting board wrong. Now, does anybody have any questions, feedback? Was that too quick? Did I lose you? Hopefully it opened up some doors here for you, or just some ideas like, hey, I should go check out OpenCV. Maybe I should play with NumPy. Hey, what is that thing? There's.
So basically, just going to
yeah.
So if you start your graph from like a state, and then you run all of your smallest domains. After doing that, and then reproduce the domain, if the domain is exactly 0, then you get just that puzzle.
Yeah, you're exactly right. That's the intuition. Is that when you're doing a constraint satisfaction problem, you're going to run into dead ends. And how do you know it's a dead end? It's when you find that you have an empty domain. Based on like the 8 went over there, guess what? This cell can't be anything anymore because that 8 went over there and it changed my domain. You're right. That's that's your check. And that's very clever of you to think that. Yeah. Good question. Yeah. Yeah, sure. Yes. Okay. Yeah, what's up, bud? Okay, that's a very good question. Okay, when you're coding something like that, remember, like it took literally 10% of the time to get to something working. And then the 90% of the time I've been spending since Sean asked me, do you want to give a presentation? I've literally spent 10 times more time because I've been making the slides and fancy graphics and actually rewriting the back code so it's actually readable. Because, when I start scripting, my letters mean nothing. I don't call it an edge. I call it a B, B1, B2. I get really lazy about, being thoughtful about, how to structure it. And it ends up being a big bunch of skitty because you're just out there trying to get it to work. And then you step back and if I think about how many times I made mistakes and crashes, I mean, this looks like, oh gosh, how do you do all that? No, I'm showing you lots of labor and iteration. So that's a good question. So it sort of worked in a different form, maybe a month ago, maybe 1 week. It didn't take that long. I mean, what happens is that you get stuck for a while, like Sudoku. I got stuck maybe 10 years. like when I first picked up Python, it was so long ago. And it was just like, I didn't have the tools or the way of thinking. I didn't know about recursion or depth first search or thinking about graphs or nothing. I was just trying to solve it. And there's only so far you can go with that kind of coding. And then when you start breaking your thinking into these building blocks, like graphs and edges and nodes and constraints, you could get a lot further. Okay, it's not that harder. It was just like you got more tools. And so I want to encourage you to think about like that, but also encourage you to just get off and just play with stuff, and just find something silly that maybe seems kind of, like, who cares? A million people have done this before. In fact, after I said, you know what, I'm sure people have done vision processing. Turns out there's a lot of blogs about how to do this kind of thing. Okay, which I haven't read. So this is my original work, but it's not that original in the sense that it's sort of obvious, like, hey, we should, this kind of interesting problem. Yes.
A few people on the chat, Tim also here,
yeah,
wanting to know how to do more of this.
Yeah.
You mentioned
yeah. Oh yeah, you're gonna get. Yeah. Yeah. Okay. So, yeah, I've been sort of charting a course by myself here in AI, and not a lot of research. I've taken a bunch of different AI courses, so it's not like I took CS50 and that was the first thing I ever knew about a neural network. I've read about this stuff before. I've tried in a different class to write the back propagation algorithm. You know, all that derivative stuff. I mean, that's where you tend to get lost, and most of the AI classes tend to go heavy into, oh, we're going to go into 50-dimensional linear algebra and you got to do all these partial derivatives and, you know, what's your step and all that kind of stuff. And you're like, hey, I sort of like this class because it says, you know, you could just stay above that level. Don't worry about it. Just this is how it works. But back to Sean's suggestion. Yeah, I would love to get a study group or a club or people interested. There's also after Math 108, there's a Berkeley class. I think it's called Data Science 100. I've been trying to like hack into that and do some of that stuff on my own. And I've said, hey, does anybody want to come with me and, you know, think together, work together on this stuff? But I just haven't. So if you're interested, reach out to me. What classes help me do this? I'm going to say like it's sort of an amalgamation of everything. What the important classes are this is, first of all, I think data structure is super important. Anything that you're doing in coding, like once you sort of want to unlayer the onion, that's, you know, it's all about data structures to some extent. And the other thing, you know, I have to tell you, 115 is a good class. 115 is a good class. I don't know why we don't teach more parts of 115 a lot earlier instead of making this big, like, oh, you got to take 150, save it all at the end. Honestly, there's so many parts of 115, we should be getting into high schools and elementary school, you know, like and or sets. Like that's real math, and it's just sort of ignored in the sake of, ooh, everything has to be f of x equals, you know, it's algebra. Algebra dominates math, but there's all kinds of math out there that's actually quite useful, you know, and makes you think differently. Remember, like when I'm looking for positions on the board, there's a lot of integer math, like div mod. What's my division and my remainder? I use div mod all the time because basically the underlying data structure is just a flat array, and I use div mod. You know, and I use a NumPy flat array, and I did div mod to find my positions. So that's true. That's true. Math 70. Math 70. Oh no. Okay. PNG. That's another very good question. Okay. The taking the picture, that's where I kind of wanted to start. Okay. The issue with taking the picture is we're going to have to do a little more image processing to get something that's like on a perspective axis. It's not going to be, this is like bird's eye view. It's a perfect 90-degree orthogonal projection, right? It's a computer screenshot, right? But yes, what you're talking about is we can apply the exact same things with a small modification. I think where the debugging would come in is finding those contours and like doing this transformation warp. CB2 has those things. I just haven't gone down that rabbit hole. Yes. Yeah. Yes. Yeah. Okay. You have amazing intuition about what's going on under the hood. And by the way, if you look at some of this code in here, it kind of is already doing that. So if you looked at one line where it did the contours, there's something called threshold, CB threshold. That's what that's essentially doing. You're basically taking above a threshold, it becomes 255. Below a threshold, it becomes 0. So you're like, it's like a hyper contrast kind of like filter. Okay. Oh, MATLAB, there's a MATLAB course here?
Yeah.
Okay, see, that's another great course. I would love to take that class. I did not even know that was available. Okay, perfect. Okay, so it's a, you know, it's a, these matrices that we're using are just, let's say, 2-dimensional arrays. Think about it that way, 3-dimensional arrays. They're not called matrices in the computer. We just call them arrays, actually. I'm just using the mathematical. I'm trying to, since I've been hired by the math department as a tutor, I thought, okay, today's talk, I'm going to throw as many math terms at you as I can, even though it's kind of a stretch. And I try to throw in that matrix multiply and the dot product and all that kind of stuff. But, you know, you sort of just like have an idea of what's going on behind the hood. And just for food thought, I would say this is so what we did was a convolutional neural network, and it's like very simple. We're doing like the most simplest task, recognizing 10 digits, right? And then like if you extrapolate what's going on in the real world about all this large language model stuff, right, that's happening to ChatGPT 4, and the process of training, you see how long it took to train. Why? Because we're telling the computer to do like a million times over and over again, multiply and add, you know, these weights, add, right? Multiply, weights, add, multiply weights, change the weights, change the weights, add. Okay. That's really what's going on in the background of these large language model training. It's sort of some like more advanced version of neural networks. I don't quite understand what's going on, but what I've been reading is that ChatGPT 3 took something like $4 million worth of like CPU and electricity to train. ChatGPT 4 is taking like over $100 million to train. And the next models we're talking about nearly $1 billion. Like it would take them like 5 months of like banks and banks of computers going 24/7 months of training. That's what's going on right now. Like, and just imagine as a grid of numbers and the computer's just sitting there tweaking them a little bit, so, you know, getting a little closer to closer. And, you know, think about it. It's sort of like, it's almost like crypto. There's a lot of just like computing happening in the background, burning up our fuel sources. So we can trade money and be lazy about doing our homework, I guess, you know, ChatGPT 4. But all right. Okay. Thank you. All right. Hey, I appreciate it. So yeah, actually, hey, this is my first talk at City College. It was delightful to be able to present again. You know, I'd love some feedback if you have any, if you want to do more of this kind of stuff. Maybe there's a way, you know, I can get pulled in somehow. Who knows, you know? Enough people clamor for me, maybe I'll even get a master's and try to teach a class. All right, thank you.